Welcome to the next video in our core quantitative methods course. In this video I'm going to introduce the normal distribution, and more importantly I'm going to introduce the foundations of statistical inference. This is relatively complicated, but it's very essential for statistical literacy because it explains how all of inferential statistics works. So maybe you need to watch certain parts of this video more than once. Please do bring any questions to class, but try to make sure to really understand the concepts I'm talking about here. So what are these things? The first thing is just variable distributions and why we should care. Then I'm going to talk about the normal distribution as the most important distribution. Then I'll go into standardizing numbers using normal distribution as a way to make sense of how big differences are, how special observations are, and then from there I'm going to move into inferential statistics. Inferential statistics is all about quantifying uncertainty. Descriptive statistics, which we've done so far, is about summarizing data, simplifying it for presentation. Inferential statistics, which will be the focus from now, is about quantifying uncertainty in two different ways. One is about statistical significance. So how certain can we be that something we observe in our sample, a difference we observe in our sample, actually reflects a difference in the population? And then the question of confidence intervals, which quantifies precision. So how confident can we be that our estimate is precise? In order to think about variable distributions and pretty much any of these other things, histograms are essential. So just a quick reminder of what histograms are. They're a way of visualizing the distribution of a variable, and very specifically, they put the values of the variable into so-called bins, into categories, and then draw a bar chart of the number of observations in each bin. Why do we look at them? Because they can actually tell us a lot more than descriptive statistics. So in this example, where I'm interested in how long batteries, for example for this clicker, last, I can have descriptive statistics. There's a mean of 145 hours, with a standard deviation we have a range. But that doesn't yet really allow me to get a sense of what's going on, what determines the battery life. If I instead look at a histogram, I can start getting a much clearer idea of what's going on. So now I know all the batteries last for 100 hours, and then there seems to be quite a consistent increase in the number of batteries that stop working. So there seems to be some process going on that puts batteries at risk from about 100 hours of lifetime, and for some reason, no of the batteries live longer than 170 hours. This might, for example, when you look at it, give you some questions about measurement. Maybe the researchers just didn't care anymore and stopped measuring after 170 hours. In any case, this histogram allows me to ask some more questions and get more of a sense of what's going on than just looking at summary statistics. That matters because the kind of thing I just talked about is what we generally are trying to understand. We're generally trying to understand what is the process by which our data is generated. If we know that, if we know what the process is, or if we have a sense of it, we know what parameters to estimate. So in the case I was just talking about with the batteries, if we actually believe that the process is that the error rate increases linearly from 100 hours, then we know that we pretty much need to estimate the starting point of the failure and that error rate, which would then give us a helpful model to talk about variable lifespan. The different data generation processes, another one, for example, would be where each observation is independent and has a constant probability. This could be identifying certain voters. If I go around the population, ask, are you going to vote for the Conservatives? Yes or no? If my sample is random, each of the people should have constant probability of saying yes. There would be one generation process. In that case, the only thing I want to estimate is that probability, which is what election polling is pretty much all about. In other cases, when my data is clustered symmetrically around a typical value, then I get into the two standard things we looked at in descriptive statistics. What is the typical value, i.e. what is the mean, and how wide is the spread? What is the standard deviation? So I need to figure out what is the data generation process. That then tells me what does the variable distribution look like, and that then tells me what do I actually want to estimate to be able to describe and understand the data generation process. The most common variable distribution is the so-called normal distribution. So that, for example, fits a distribution of people's height, but it also fits many other processes of interest. So very often we will find data that fits the normal distribution, and then we have a lot of helpful tools to work with it, because it's such a well-established type of data generation process. Another example is birth weight. So this is the weight of babies born in a hospital, follows the same kind of shape. This is the monthly average stock returns over almost a century. Even though here it's actually important to note that it does not follow a normal distribution, because I cut something off. The standard processes follow a normal distribution, and then there are a couple of outliers all the way off the screen of months that had large stock crashes. So sometimes we might get too lulled into thinking everything follows a normal distribution, but still, apparently a large part of the stock market activity does follow a normal distribution. IQ scores are a common example, and that they follow the normal distribution isn't surprising, because that's how they are defined. IQ scores are defined as having a mean of 100, a standard deviation of 15, and following a normal distribution. However, the reason they are defined that way is because there's good reason to believe that something like intelligence is normally distributed. Test scores often work in similar ways. SAT scores to access American universities, for example, also tend to be normally distributed. Why is it that we see so many of them? Well, it's because a combination of random processes very quickly leads to a normal distribution. So if I throw a single die, I should get a flat distribution, the same number of 1s, 2s, 3s, 4, 5, 6. Flat line. One random process doesn't give me a normal distribution. When I combine the sum of two dice, I get a distribution here, which already looks quite normal. So when we look for a normal distribution, we're looking for a nice hill that's symmetric. It's clearly not rounded, so it's not a fully normal distribution. If I keep on adding some additional random processes, in this case I need about 4 dice, and I get a very nice normal distribution. So if we now think about height, about intelligence, how is that generated? Well, it's lots of different processes that add up. Nutrition, genes, the environment, parenting style, education, all of these things just add up. Variations between them are somewhat independent, so the result will be a normal distribution. A very specific kind of random process that we're very interested in the context of statistics is random sampling. So when I try to figure out what a normal distribution looks like, I only need to estimate these two parameters that we talked about earlier. We need the mean and the standard deviation. They're quite often expressed with the Greek letters mi and sigma. If I know those two, I can plot the curve, and I can now place any particular value on that curve. Why is it helpful to be able to place values on that curve? Well, because it allows us to estimate how special observations are. So if I just tell you, I have this friend who has an IQ of 130, what does that really mean? Is it a particularly intelligent person? Is it just a person who's slightly more intelligent than the average? What does that mean? Fortunately, when we are on a normal distribution, it's quite clear what that means, because there's very specific empirical rules about how many values fall into a specific range. So my friend with the IQ of 130 is 2 standard deviations above the mean IQ, by definition. And now I can look at this chart and see that only 5% are more than 2 standard deviations away. So being so far away from the mean is actually pretty special. This also then tells us 3 standard deviations encompass 99% of our sample. So it tells us pretty much the relevant range of normally distributed data. So it's helpful to know the shape of our data because it allows us to estimate how special specific values are. That's fairly easy to do with something like IQ because we know the standard deviation, we know, so we can very easily compare these values. How do we now compare completely different values? So how special the weight of a newborn is compared to, for example, this IQ? Well, we just convert those values into standard deviations. So an IQ of 85, on the other hand, that would just be 1 standard deviation below the mean. So this would be a value of -1. A newborn of 4 kilograms, well, that would be 1.1 standard deviations above the mean of the data that I showed you earlier. So now we have 2 numbers that express how special these values are. And we can compare them and say, well, this baby is actually a bit more special than this person with an IQ of 85, a bit more out of the norm. Of course, in this example, it's a bit trivial. In other cases, it might be really good to be able to compare different things. So is gender discrimination more prevalent when it comes to salaries? Or is it more prevalent when it comes to hiring decisions? And this idea of converting it into standardized values, or so-called Z-scores, now allows me to compare these completely different domains. Z-scores don't have units, so any 2 of them are comparable. In real life, they're quite often used as benchmarks when we want to decide how special something needs to be classified in a certain way. So for example, the World Health Organization uses them to classify children as malnourished or as stunted by saying, in the very particular distribution at any age and gender, how extreme does the observation have to be? I.e., what Z-score does it need to represent for us to say, well, this child is actually obese or is actually stunted? Z-scores then also help us to compare different effects. So we might ask, is the gender effect, the difference between men and women, greater with regard to weight or to height? One of them will be expressed in centimeters, one of them will be expressed in kilograms, so we can't directly compare them. In the case of height, we have this difference between men and women. We can pool the standard deviation, that's just the average standard deviation between the 2 samples, and then we can calculate what the Z-score is. We can do exactly the same for weight. And then again calculate the Z-score, and now we're able to compare weight and height. The largest score here shows that that variable shows a greater difference between men and women. So in this case, in the Canadian Fitness Survey quite a while back, there was a greater height difference between men and women than weight difference, which might tell us something about differences between the male and female body. So this much about distributions and about standardizing values and then using, particularly the normal distribution, to make sense of values of different variables. Now moving on to inferential statistics. Inferential statistics is no longer about describing the data set that we have, but it's about moving from that particular data set, it's usually just a sample, to the full population. And if we do that, there are usually two types of questions. One of them is a difference in my sample reflective of a difference in the population? So, for example, on my exam, I might see that girls perform better than boys. Is that likely to be reflective of a difference in performance in a broader population among students who didn't happen to sit that particular exam? That's called significance testing. The other question might be, how confident can I be about my estimate of the gap between two groups? So on my exam, boys might have scored 10 points more than girls. But how confident can I be about these 10 points? Even if I say there's a difference between the two groups, might it be 1 or 100? Or is the 10 quite a precise estimate? That's where we want confidence intervals. But firstly, about significance. We might have this research question whether men have more sick leave days than women or the other way around. We might collect some data from a sample of employees at a company, and then we get these two values. And these two values, these descriptive statistics, tell us that women on average take 2.7 days off sick, men on average take 3.5 days off sick. So for our sample, the answer is clear. Men have more sick leave days than women. However, no one is really interested in the answer about these 6 men and 6 women. The interesting question is, what are we able to say about all the employees of that company? And clearly, we can't now just say that this applies to the whole population, because if we replace our research question and say, well, are men better at throwing dice than women? Do they get higher scores? We might end up with exactly the same numbers, and in this case, quite clearly, we would not conclude that men are better at throwing dice. So why not? The logic of statistical testing is that once we have that difference, we need to figure out how likely it is that it was just due to chance, or if it is likely that it was just due to chance. And the way we do that is by asking, if there was no difference between men and women in this case, how likely is it that we would just by chance have observed the data that we observed? In that condition of there being no difference is what we call the null hypothesis. So, assuming there's no difference between men and women, how likely would it have been to see this difference between 2.7 and 3.5? In a dice throwing example, we can fairly easily figure that out by saying we just throw 12 dice, we split them randomly into 2 groups, because then there's definitely no difference between the 2 groups. We calculate the 2 means, and if we do that quite often, we can get a null distribution. If we do that with a computer, quite conveniently, we can simulate this. Here we had simulated 1,000 rolls of 12 dice, then randomly split into 2 groups. And this shows this is again a histogram that shows how often we found a specific mean difference. In our example, we had observed a difference of 0.8. I've indicated where 0.8 would fall into that distribution. Now we already visually see that's actually not very special. So in this case, clearly we can't say it would have been unlikely due to chance. We see in this distribution generated by chance, it's quite close to the middle. We can also notice that this distribution of means follows the normal distribution quite nicely. And that is because of something called the central limit theorem that says, actually, regardless of what distribution you draw your sample from, if it's a flat distribution, if it's a distribution like the battery one, which is called a logarithmic distribution, or it's a normal distribution, regardless of that, if you draw more than 30 participants, then the distribution of the summary statistics will be normal. And that's very helpful because it allows us to use the normal distribution to describe many processes that are not normal. So the central limit theorem, just so that we have heard this. Now the more important question is, how do we move from this visual intuition we just had, saying, well, 0.8 is quite close to the middle, so it's probably not very, very special. How do we move from that towards a formal test, a formal rule, for whether or not we believe that this difference is due to chance? Well, we reject the null hypothesis if it's sufficiently unlikely that we would have observed this data. If we reject the null hypothesis, we say it's not true that there is no difference, so then we accept the idea that there is a difference. How do we now move away from just discussing this and having a decision rule that we can agree on collectively? Well, we first need to be able to calculate the probability very specifically that we would have observed this value under the null hypothesis. That's then called the p-value. I'll show you in a moment how it could be calculated in this particular example. But we have a probability now that this data would have been observed under the null hypothesis. How small does the probability have to be for us to say, now it's sufficiently unlikely to accept that it looks like there is a real difference? Well, thinking about coin tosses, how soon would we think that something fishy is going on? Clearly tossing one coin, no information. Tossing a second coin that again turns up head, chance. Third coin, well, still kind of seems reasonable. Fourth coin, something might be going on. Fifth in a row, This is the point, and not because of coin tosses, but because of convention, but this is the point where we would say, this is very unlikely to be due to chance. Let's investigate. Let's say for now we have grounds to be very suspicious of this coin. That is specifically called the alpha level, this level at which we say we reject the null hypothesis, we believe that something is going on. And conventionally that's set at 5%. And 5% is approximately the probability of tossing 5 heads in a row with a coin. So how do we get p-values? We need them to then decide if they're higher or lower than 0.05, than 5%. If we can simulate the null distribution, as I just showed you before, then we can basically just count how many of the simulated samples are further away than what we observed. And then those samples, as a share of all samples, would indicate how likely we are how likely we are to observe something as extreme as what we saw, just due to chance. Usually, we decide to play it safe and take samples that are as extreme in either direction. So we would say, how likely are we to have an absolute difference of at least 0.8, positive or negative? If we do this, we see that in 46% of the cases, we would observe a difference like this due to chance. Clearly 46% is a lot more than 5%, so we would not conclude that there's a difference between men and women on their ability to throw dice. And note that this doesn't have to be a mean difference between two groups. This could also be a correlation coefficient, it could be a range, it could be any descriptive statistic that we want to test. How do we actually get p-values in reality? Well, we don't always simulate. Quite often, we just rely on existing distributions. One of them is the t-distribution that's very similar to the normal distribution, but just accounts for sample size. And then basically, we look up where we fall on a distribution and look up an associated p-value. Clearly, we don't do that anymore. That used to be done actually in statistical tables. Now it's done by the computer. In some special cases, we still have to do simulations. For some special statistics or special distributions, there are no established p-values, so then we need to simulate and look them up. So, to sum this up, to answer this question, does the difference in our sample reflect the difference in the population? We tend to do null hypothesis significance testing. There are other ways to do it, but this is the main one and pretty much the only one we cover in this course. So, to approach the question, we consider the counterfactual or the assumption that there would be no difference between the two groups. And then we ask, how likely would we have been to observe the difference we observed if that assumption was true, if there was actually no difference? And once we know that, we then decide, is it sufficiently unlikely that we can reject our null hypothesis, or is it not? What flows from this approach? Well, the first key idea is that we never know the truth of our hypothesis. We can only make claims based on probability. And we don't know how likely our hypothesis is to be true. We only know how likely it is that our observation would have occurred under this chance condition. We know how compatible our data is with the null hypothesis. So, as in any such probabilistic situation, statistically significant results might arise due to chance, and we might not find real differences, again due to chance. And also quite importantly, statistical significance isn't the same as practical significance. If we find a statistically significant difference, so if we are able to reject the null hypothesis because our data is not compatible with that, then we say we have good reason to believe that there's a real difference between, say, men and women on the level of empathy. In real life, the important question then is the difference large enough to actually be of interest? And that's what practical significance is about. It's a separate step to then talk about. So we talked about the first main question in inferential statistics. Is it likely that if we observe a difference in the sample, that there actually is a difference in the population? The second question is, what's the kind of range of values in the population that we can expect based on our information from the sample? So how good is our estimate? We generally want to estimate some value in the population based on our sample. For example, again, in the case of an election poll, our sample tells us that a certain number of them want to vote for a particular candidate. Or we might do a study on Instagram use. Our sample tells us that they spend a certain amount of time on Instagram. And if we have no sampling bias, then this gives us a reasonable estimate, or this is the best basis for forming an estimate about the value in the population. So if 20% of our sample say, well, we'd like to vote for candidate A, then these 20% are a good starting point for estimating something about the population. Similarly, if our sample of Instagram users says, well, we spend 40 minutes a day on Instagram, that's a good starting point for estimating how much time the larger population spends on Instagram. But we still want to know how good an estimate is it. How close do we expect the true value to be to our point estimate? If we had luxury of having many, many samples, if you could now get not just this one sample of 100 Instagram users, but 1,000 samples of 100 Instagram users, then we could plot the results from these 1,000 samples, and we again see a distribution. Some of the samples, by chance, have rather low average Instagram usage. Some of the samples have high average Instagram usage. So what can we tell about the population from here? We can figure out whether the lowest 2.5%, what are the highest 2.5%, and what are the 95% in between. So if we calculate just two values, we can highlight them on the plot, and then we can say, well, our true value is very likely to be in between those two, right? 5% chance to be outside, but 95% chance to be in between those two. Those two, in this particular case, range from 37 minutes to 43 minutes. And then we could say, well, we have a 95% likelihood that the population value is actually inside that range. In reality, unfortunately, we only have one sample. So we can maybe replicate the study a couple of times, but we can't get our confidence interval by running the study many times. That's just not feasible. And inferential statistics is about moving from one sample to the population. How do we generate many samples out of one? That's the idea behind bootstrapping. And the intuition here is that in our sample, we're likely to have all the relevant user types. So a sample of 100 will have given us some power users, will have given us some users who rarely use Instagram. So the assumption of bootstrapping is we have all kind of relevant types inside our sample. And then we say sampling error actually comes from the fact that the distribution of these relevant types is likely to be off. So to create new samples, what we do is we take participants out of our existing sample, but we do that with replacement. So some of the participants from our current sample will show up more than once in our new sample. The new sample has the same sample size as the old one, but it's 100 people sampled with replacement from the original population. From the original sample. This new sample now gives us a new sample statistic. So a new average time of Instagram use. We do this many times to get many bootstrap resamples of the original sample that all have the same size. We calculate all of the summary statistics, in this case the average time spent on Instagram, and then from there we can plot those summaries and do what we did before in terms of finding the range within which 95% of those samples are. That's what bootstrapping confidence intervals is about. So I simulated 1,000 bootstrap samples, sampling only participants who were in the first sample. I could again draw up these two numbers, and actually we get very similar confidence intervals. We don't get the same, and probably the first ones would have been more correct because they're based on just a lot more information. But this is something we can realistically do. This only requires data from one sample and then a statistical analysis. And this kind of bootstrapping, this kind of resampling from our existing sample to estimate a confidence interval always works for any statistics. So we can create a confidence interval for the median, for the standard deviation, for the range, for correlation coefficient, for minimum value, maximum value, whatever you like. But historically, this could be done very rarely because it takes a lot of computing power. Usually we wouldn't do 1,000 resamples, but rather something like 10,000. Modern computers can usually do that very easily, but bootstrapping has never become the standard in statistics. I would say in large part because of historical restrictions on computing power. So how do we calculate confidence intervals? Well, if we know that our statistics follows an established distribution, then there are formulae to do that. So we know 95% fall within 2 standard deviations of the mean in a normal distribution. So if we know our test statistics follows a normal distribution, it's not very difficult to calculate a confidence interval based on that. And that's how statistical software generally produces confidence intervals for us. You don't need to know any of these formulae, but when you run statistical tests in R, you will quite often get these calculated confidence intervals. Unless the output says anything about bootstrapping, you can assume that it's based on a formula. For some statistics, such as already a median, we do need to use bootstrapping because there are no formula. So how are the two aspects of inferential statistics connected? Now, significance testing tells us, loosely speaking, are we 95% sure that a certain value is different from 0? So for example, the difference between two groups. Confidence intervals tell us what is the range within which we can say with 95% probability that we can find our value. So quite clearly, if that 95% range doesn't include 0, then we can conclude that there is a significant difference. Why do we do statistical testing? Well, because it gives us a more precise estimate of the probability. And that's of course good to know whether we have a 5% probability or a 0.1% probability. But in essence, if the confidence interval doesn't contain 0, then whatever the confidence interval is for is statistically significantly different from 0. There are some weird cases when those two analyses give us contradictory results, and those are then definitely cases to look a bit more closely at the data and try to see what's going on. I note that both of these definitions of statistical testing and confidence intervals aren't technically correct, but they are the intuitions you definitely should take away. So, what to remember? It's helpful to look at the distribution of a variable because that gives us information about the data generation process, and the data generation process tends to be what we are most interested in. Then variables that are created by a combination of random processes, such as height influenced by all kinds of environmental factors, they tend to follow a normal distribution, and the normal distribution is fully defined if we know the mean and we know the standard deviation. Normal distribution is particularly helpful if we remember these handy rules of 2/3 of the variables falling, 2/3 of the observations falling within one standard deviation from the mean. Basically, all variables falling within 3 standard deviations, and 95%, which is exactly our usual significance levels, falling within 2 standard deviations. So with that, we can quite quickly then get a sense of the plausible range for our variables and how special certain observations are. To get an even better sense of how special certain observations are, we have z-scores. Z-scores are our value divided by the standard deviation, and the value here being the distance from the mean, so our distance from the mean divided by the standard deviation, and that allows us to compare how special values are from very different distributions. What else to remember? So inferential statistics is about going from one sample to the population and quantifying our uncertainty in that generalization step. So significance tests as a part of that just test whether the statistic we're looking at, for example, a difference in means, is unlikely to have arisen due to chance. So we posit a null hypothesis of no difference, see how likely that would have been to result in the data that we see. And then, if that's very unlikely, for example, less likely than 5% in most cases, we say the null hypothesis, this hypothesis of no difference, is very likely to be false. So let's accept the research hypothesis, the hypothesis that something is going on here. Confidence intervals, on the other hand, allow us to estimate the range in which our value is likely to be. And then lastly, bootstrapping is a very helpful tool for creating confidence intervals, is resampling many times from our original sample with replacement to estimate the sampling variability and thereby estimate our confidence interval. Please now write down any questions that you might have on this so that you actually remember them in class. And then we'll spend some time making sure that we're all on board with all of these concepts. See you there.